Hello, hi. In this video, I'm going to talk about the normal probability distribution. My name is Emmanuel Madanga and I'm from Beyond Data Statistics Solutions. Kindly subscribe to our channel. We usually have a lot of statistical aspects that we cover in this our channel. So the normal distribution is the most common probability distribution in statistics. As you can see, it takes the normal curve, which is bell-shaped, with a mean of 0 and standard deviation of 1. So that is it, a sketch of how the normal distribution looks like. So when dealing with normal distribution, we are interested in computing some scores out of it that help us in making decision. So the first aspect in the normal rule, that's normal probability plot or distribution, is the empirical rule. The empirical rule is a rule that tells us about where an observation lies in a normal distribution. So this one, what it does particularly, it's just about the distribution of observations around the mean. And as we can see, the first standard deviation, that is one standard deviation, tells us approximately it is 68% of the data will be within that one standard deviation of the mean. And when we talk about the two standard deviation, as we can see on our screen here, that probability from the two standard deviation, that is the positive, to the two standard deviation, that is negative, is 95%. So what does it tell us? It tells us that 95%, about 95% of our data will be within that the two standard deviation of the mean. And lastly, on the same perspective, we can observe that about 99.7% of the data will be within the third standard deviation of the mean. So here is an example of how to make use of the empirical rule in the computation or solving out of a particular problem that you may have. So the first thing that you can have, like in this case, suppose the height of males at a certain school is normally distributed with a mean of mu, which is 70 inches, and a standard deviation of sigma is equal to 2 inches. So maybe approximately what percentage of males at this school are taller than 74 inches. So by the use of the empirical rule, we can be able to estimate the approximate percentage of male students in that particular school that are likely to have a height of more than 74 inches. So maybe you have a sketch. We have a sketch of how this distribution looks like. Then from there, we are now going to locate where 74 inches is. Specifically from our previous overview about the empirical rule, you can see easily that 74 based on the mean. So mean is at the center. Then the distribution of the data is 2 inches away from the mean. So the first standard deviation will be at 72. The second standard deviation will be at 74. So what does that tell us? That one tells us that 74 is located on the second standard deviation. Let's see the sketch for that. So we can see here that the mean is at the center, and then our first standard deviation is 72. That 72 is at our first standard deviation, and then we have, which is approximately 34%, that is immediately to the positive side or above the mean. And then the probability of 74 from the mean is 47.5. Just you add 34 plus this, you get that probability. But when you want to get the probability that the students are likely to have a mean that is greater than 74. So that will imply, or taller than 74, that will imply that that's the region, the rejection region that might be of interest. So we look for that probability, which definitely we can obtain it by taking, because we understand from 70 going to the right is 50%, and 70 going to the left is 50%. So we can just take 47.5, then you subtract that 50% and 47.5%, and you get the total probability or total percentage. Yeah, the total percentage that observation is likely to fall in that category for 74. Yeah, alternatively, you can just do the way I did here, just sum the remaining probabilities. Definitely we understand how this distribution flows from the mean. Yeah, so you just sum the two and you obtain that probability. So you have two ways. The first one is to take 50, the probability 50% from the mean. I have subtract 47.5, which is just the sum of this probability. That's just taking this probability minus the entire probability, the entire percentage, approximation of that percentage. Yeah, and that is it. So that is the probability there. So, and again we have the other aspect of z-score. So maybe working with the empirical rule is may happen to be challengeful to most of the students. So we have z-score that we use to perform the same task. Yeah, like in this case, this question was straightforward, and maybe you may encounter questions that does not lie exactly on the any of the standard deviations, that is, does not lie on any of the empirical rule. So you may get a challenge on that. So you just make use of z-score. So it can be helpful in doing that. So I will describe what z-score is all about and how it is computed. So z-score is just a statistical measure that quantifies how far a data point is from the mean of a data set, that is. So in terms of the standard deviation, so it is it really depends on the standard deviation. So that's why you see the key factors here in the computation of the z-scores is the standard deviation and the mean, which is mu, and then the data point can come in, data point x can come in, and now this is our formula for the computation of the z-score. So where z is the z-score itself, x is the data point for which you want to calculate its z-score, and mu is the mean of that data set. Then you can now have what we call standard deviation, which is sigma. Yeah, you are given in a question, so you just obtain it there. So to use the z-score, follow the following steps, or definitely this one really illustrates. What you just have to do is to substitute whatever you have for mu, for sigma, and for x in that formula. Yeah, just plug in the values into the formula. Then the resulting score tells us how many standard deviation the data point is away from the mean. And to note on the same is that a positive z-score indicates that the data point is above the mean, while a negative z-score indicates that the data point is below the mean. Yeah, so z-score can take any value as either positive or negative, where positive will indicate that the observation or the data point is indicates that it's above the mean, while z-score that is negative just indicates that the data point is lying on the lower side of the mean, is below the mean. Yeah, so z-score is commonly used in statistics to identify outliers and to compare values across different data sets with varying means and standard deviation. So any data that does not lie in the any of the 3 standard deviations, then that data may be considered as an outlier when you have enough sample size. Yeah, that one can be considered as an outlier. So why do we need this formula? You see, working with the empirical rule, sometimes it is inappropriate when you find out that your data point does not lie on any of the 3 standard deviations. So the use of Z-score comes in very handy. That helps us to standardize the data and understand its relative position within the distribution. So here are some of the common situations where Z-score formula can be applied. Yeah, so these are some of the common situations. For example, the detection of the outlier. Yeah. Often, as you can see, it helps us identify the data points that are significantly different from the mean, or significantly away or weird observations. Yeah, or extreme observations. That is what outlier is. So if a Z-score is much higher or lower than certain threshold, yeah, often around plus or minus 2 or plus or minus 3, it indicates that the data point is an outlier. Yeah, so then from there we have the normalization and standardization. These are cases that we use. Yeah, Z-scores are used to normalize data by converting different scales of data into a standard scale. So this is especially important in machine learning and algorithms where features might have a varying range. So these are some of the situations that we make use. Yeah, for example, maybe comparing different data sets when dealing with data in different means. We can also use Z-score to allow us have a fair comparison. In quality control, we do the same to detect defects of the data points that are significantly from the expected values. Even in the financial analysis, we carry out Z-scores to help us predict the likelihood of the bankruptcy. Yeah. In psychometrics, that is in psychology assessment, it helps us also identify the individual's performance. Yeah. To reference to a group. That's control and so on. So in grading and evaluation, it also helps us do that to compute class mean and compare the performance of each student based on what we have as a class. And maybe in research and data analysis, Z-scores are fundamental tools in statistical analysis used to understand the distribution of data. Yeah, and that's why we are learning it. So those were some of the key aspects that Z-score really help us carry out. So if you are Z-score really assumes that the data follows normal distribution. So if your data is not normally distributed, then it is not appropriate tool to use for data analysis. So in summary, Z-score formula is a versatile tool that helps us standardize and compare data across different complex and disciplines, making it fundamental concept in statistics and data analysis. So yeah, how to draw it, we have seen that, and maybe we have an example on how to do that. Suppose you have a patient, a hypertension patient, with a mean of 150 mmHg and a standard deviation of 10, and you want to look at the distribution of that person, and maybe you want to determine if this individual, the probability that the person's, maybe a patient is selected at random from this population, and you want now to determine if the probability that a patient may happen to have a greater SBP, yeah, compared to that one of the mean. So we use this Z distribution to do that. So the peak of the value is the mean value of the mean, that is 150, and the curve is symmetric around the mean. As you move away from the mean, the density of the patients decreases. Yeah, that is the concentration of the patient decreases as far as you move away from the mean following the 10 mm Hg. So calculating that probability that maybe a patient is likely to get to have a greater SBP than the mean, which is 150, of greater than 150, which is just equal to the mean. So you understanding the distribution of our sketch, how the data is distributed. From the mean going to the right is 50%, and from the mean going to the left is 50%, which is approximately 0.5 when you convert it into probability in terms of decimals. So if you want to find the probability that a random selected patient will be having a greater than 150 mm Hg, in other words, you want to find the area under the curve to the right of the value 150, that is. So since this is a standard normal distribution with a mean of 150 mm Hg and a standard deviation of 10, so you just substitute in your Z formula. You don't have to worry. So in your Z formula, you substitute everything, you'll get a Z score of 0. A Z score of 0 corresponds to the mean of the distribution. Yeah. So when looking up the probability in this case, so the cumulative probability will be 0.5. That is the probability that patient is likely to have a mean greater than that. Even if you look this Z score from the Z table, you should be able also to get the same probability. Yeah. So if you can see my Z table here, so a Z value of 0, that is 0.0, is approximately having a probability of 0.5. Yeah, so that is it. That is how we look at our Z table. So you have to come here and this column, look for the value 0.0, then you come to the first point where we have a value of 0.5. So that one gives us that probability. So that is traceable that way. Yeah. So therefore the probability that a random selected patient will have SBP that is greater than that 150 is 0.5. In other words, you can say it is 50%. Thank you so much for watching my video on normal probability distribution. Okay, thank you.